Hello and welcome to lecture 13 of the course Theory of Computation. In the previous lecture, we saw pumping lemma for regular languages, right? So we saw what the pumping lemma statement was, and we saw the proof of the pumping lemma. In this lecture, we will see how it can be used to show that some languages are not regular. So just to recap, pumping lemma is a necessary condition for a language to be regular, and we can use pumping lemma to show that languages are not regular. Okay, so it's a necessary condition. So meaning, if a language is regular, it has to necessarily satisfy the conditions of the pumping lemma. So you can take a language and show that it does not satisfy the conditions, and hence it is not regular, right? Just because it satisfies the conditions does not imply that the language is regular. So this is very important. You can use pumping lemma to only show that languages are not regular. Okay, you cannot use pumping lemma, okay, to show that languages are regular. Okay, so just because it satisfies the condition doesn't imply that the language is regular. What you can infer is that because it does not satisfy, the language has to be necessarily not regular. Okay, so this is what pumping lemma is. And this is what it can be used to show. So just to recap, pumping lemma states that if A is a regular language, there is a pumping length such that any string S that is a member of A and of length at least the pumping length, right? So pumping length here is P, right? Then we can split S into three pieces X, Y, Z such that it satisfies the three conditions. The three conditions are one, that x y power I z is in A. So x y power I z could be having 0 repeats of y, 1 repeat of y, 2 repeats of y, 3 repeats of y, and so on. It's an infinite set of strings. Second is y is not an empty string, and third is that the length of x y is at most p. So usually this is the sequence of things that you do when you want to show that a language is not regular, right? So what you say is, if you are given a language, you first, so pumping lemma says that if the language is regular, it meets these conditions, right? So you assume that the language is regular. Suppose you are given a language and you want to show that it is not regular, right? So you assume that the language is regular, and because the language is regular, or because you assume that the language is regular, pumping lemma implies that there is a pumping length, right? So let's call that pumping length P. Now choose a string in the language, okay, and the string has to be of length greater than the pumping length. Okay, so usually the pumping length, we don't know what it is. We can just assume that it is some variable p, some parameter p, right? So this string can depend on the p itself, right? So it could say, it could have p in its description, like, even though we don't know what p is, right? And you choose a string that is of length at least p, that is in the language as well, and show that this string cannot be split as x, y, z, satisfying the conditions of the pumping lemma, right? So pumping lemma says that any string that is in the language of length at least p can be split satisfying these conditions. So to refute that, so you want to show that the language is not regular, you want to arrive at a contradiction. So you take a specific string, okay, this is completely our choice or your choice, right, and show that there is absolutely no way that it can be split into x, y, z that satisfies these three conditions. Okay, so that is a rough game plan that we have, right? So again, I want to reiterate two things. One is that the choosing of the string, that is usually the most important step, and it's also the most creative step involved. The rest follows fairly systematically. This is where one has to probably get a bit creative, right? So the string could be anything. It can be any string that we like, which is in the language and is of length at least p. But then the choice of string is entirely our choice. But once having chosen this string, we have to show that there is absolutely no possibility of breaking this string down into x, y, z which meets these conditions, right. So, we have to rule out any possible split of x, y, z, saying that if you split it this way some condition gets violated, if you split it that way some other condition gets violated, and so on. Okay. So, you have to only pick one string, and for that string we have to show that none of the splits satisfy the conditions, and that is how you get the contradiction, right. So, maybe let us see an example and that will make things clearer. Okay. So, the first example, which is the most common language that is not regular, okay, is B, which is 0 power n, 1 power n. This is the same as the language. So, where n is 0 it is the empty string, where n is 1 it is 0 1, then 0 0 1 1, then 0 0 0 1 1 1 and so on, right. So, this is the language. So, we go by what we said already. We first assume that this language is regular. Okay. Now, there is a pumping length p. So, now let us choose a string that is in the language and is of length at least the pumping length. So, here I am going to choose 0 power p 1 power p, which is basically p zeros followed by p ones. So, this is clearly in the language, right. So, the language is any number of zeros followed by the same number of ones, right. So, the language is an infinite language, right. So, you could have 2 zeros followed by 2 ones, 3 zeros followed by 3 ones, 4 zeros followed by 4 ones, 5 zeros and so on, right. So, it is an infinite language. So, like that whatever value p is, we have the string p zeros followed by p ones, right. So, this string is clearly in the language and it is of length 2p, right. So, there is p zeros followed by p ones. So, it is of length 2p. So, it satisfies both the conditions, right. Now, pumping lemma says that since this string is in the language and since we assume that the language is regular, we can split this into x, y, z satisfying the three conditions. Now, we will show that it is not possible. So, let us see why. So, what is S? S is all zeros, p zeros followed by p ones, right. This is S. Now, suppose y. So, now if we split into x, y, z, so y could, so there is x followed by y followed by z, right. So, y could be entirely in the 0 part. If y is entirely in the 0 part, let us say y is somewhere here, right, then the problem is that, so condition 2 says that y is not an empty string. So, which means y has at least one 0, right. So, if you consider x y square z, let us say I call S prime as x y square z, right. If you consider x y square z, or in other words x y y z, so this has one more y than what S had, which means S prime has more zeros than ones because y is entirely zeros, right. So, when you add one more copy of y, the resulting string has more zeros than ones, but we know all the strings in the language B have the equal number of zeros and ones. So, this S prime is not in the language. So, this is not in the language. The same thing holds when y is just entirely in the ones. So, suppose y was entirely in ones, right, somewhere over here, then not the same thing, but similar thing, because we again consider S prime x y y z. Again, because of condition 2, y cannot be empty. So, y has to have at least one symbol, and we are by assumption y is only, by the assumption of this case, y is only ones. So, x y y z will have more ones than zeros, because x y z had the equal number of zeros and ones. When you add one more copy of y, you will end up having more zeros than ones, sorry, more ones than zeros, right. So x, y, z has the same number of zeros and ones, and y has entirely ones, and when you add one more copy of y, you end up having more ones than zeros, right. So this is what happens when y has only ones. So even this string is not in the language, right, because y has only ones also is not in the language. Now consider the third case. So the three possibilities are y is only zeros, y is only ones, and the third one is that y contains both zeros and ones. So just to denote in the figure above, so maybe y transcends the boundary of zeros and ones. So y comes something like this. So y is some zeros followed by some ones, right. So something like this that I have written here. So now consider S prime, which is again x, y, y, z. So if y is transcending the boundary, x has to be entirely zeros and z also has to be entirely ones, right. Y is crossing the boundary. So x has to be entirely zeros and z has to be entirely ones. So now let us see what shape x, y, y, z has, right. So it will have x which is entirely zeros, y which is zeros and ones, some zeros followed by some ones, right. Then again another copy of y which is some zeros followed by some ones, followed by z which is entirely ones. So basically you start with zeros, x and the initial part of the first y, then you move to ones, then again you move to 0, the initial part of the second y, then you have entirely ones. So it is like some zeros, some ones, some zeros again followed by ones till the end. So this is some zeros, some ones, some zeros, some ones, right. So this is not, so if you look at the language B, it is all some zeros followed by same number of ones. This, so in other words, B is a subset of 0 star 1 star, right. But this string here x, y, y, z, right, this string over here that I have, right, this is not of the form 0 star 1 star. Hence this S prime is also not a part of B, right. So this means we took a string S which is 0 power p, 1 power p. We wanted to show that it cannot be split in the as x, y, z meeting the three conditions. So there are three possibilities for y. Y is entirely zeros, entirely ones, and a mix of zeros and ones, right. What we showed is that each of these three cases there is some contradiction that we get, and x, y, y, z is not in the language B. This means that there is no way to split x, y, z, there is no way to split S as x, y, z meeting the three conditions, or in sometimes informally we refer it to as there is no way to pump the string. Okay, so pumping means we cannot split it in x as x, y, z meeting these three conditions. So this string there is no way to split, and hence B is not regular. If B was regular, all strings that are in B and that are of length greater than P can be split. However, this string cannot be. Hence, B is not regular. Right. So we assumed that B is regular. Then we assumed a pumping length. Then we chose, again this is entirely our choice, one string 0 power p, 1 power p, and showed that there is no possibility of splitting it as x, y, z that meets the conditions. So this is the usual template of what we follow when we want to show that a language is not regular. So notice one thing here, we used condition 1, like because condition 1 says that x, y power I, z has to be in the language, right. So x, y power I, z. So we use that in all the three cases. We also used, even though I didn't make it very explicit, we also used condition 2, because condition 2 says that y is not empty. if y were like we are using that to say in this case, in the first case we are using that to reason that y has at least one 0, because if y is empty string, that right, that does not make sense. So, we are using condition 2 that y is non-empty in all these 3 reasonings. However, we are not using the third condition, right. The third condition says that the length of xy is at most p. If we had used the third condition, so right, if we had used the third condition, the length of xy is entirely p, and we know that xy is the initial part of the splits, right. So, x, y, z. So, z is the last part, x and then y and then z, right. So, if xy is entirely p, the first the first p symbols, right. So, in fact, xy is at most, the length of xy is at most p, right. So, it not even be p symbols, it could be less than p symbols. This means that xy is entirely contained in the 0 part. This means that y is also entirely contained in the 0 part, and this means that we necessarily have to be in case 1, like case 2 and 3 don't even aren't possible because of condition 3. But then if you come to case 1, then again, like we reasoned above, x, y, y, z has more zeros than 1s, and hence it is not in the language, right. So, this is another way to like if you use condition 3, we get a different chain of reasoning, but still we end up with the same inference that we cannot split y as, sorry, we cannot split x s as x, y, z satisfying the 3 conditions. Okay. Now, let us consider another language, C. Okay. C is a set of all strings, binary strings, that has an equal number of zeros and ones. Okay. So, B also was a set of binary strings that have equal number of zeros and ones, but B required this structure. We have all the zeros and then all the ones. C does not require all the structure. So, it could be any string. So, for instance, C could contain 0 1, 1 0, 1 0 1 0, like 1 0 1 1 0 0 1, like anything that contains, sorry, not the last one, right, anything that contains equal number of zeros and ones, right, like it could be mixed in any order, any sequence, right. Right. Also, the empty string has 0 zeros and 0 ones, right. Now, let us try to show that this language is not regular. So, it is the usual thing that we already saw. We assume it is regular, then there is a pumping length, and then we have to choose a string. Here again the same string is good enough, 0 power p, 1 power p. So, where p is the pumping length, right. Clearly, this has equal number of zeros and ones, p 0 is followed by p 1s. So, hence it is in the language C. Also, it is of length 2p, which is at least p. Hence, this has to be this can be pumped, meaning this can be split as x, y, z, meeting the 3 conditions. Now, let us look at the string, right. So, this string is p zeros followed by p 1s. Condition 3 of the pumping lemma says that xy is of length at most p, right. So, this is what condition 3 says, xy is of length at most p. This implies that since xy is of length at most p, this implies that x and y are entirely in the initial p symbols, which are entirely zeros. Hence, it follows that xy is entirely zeros, right. So, the number of zeros could be p, it could be less than p, right. Since xy is entirely zeros, y is also entirely zeros. Let y be like some number of zeros, let us say L zeros, right. And by condition 2, we know that L is at least 1, y cannot be empty string, right. So, condition 2 implies that L is at least 1. Hence, we know that y is some string of zeros of at least 1 zeros. So now consider the string, we use condition 1, which is x y power I z. So now consider x y power I z, y squared z. So x y y z. This contains, so x y z contains equal number of zeros and ones. We add another y which is entirely zeros, right. Now, so which means this will contain L more zeros than ones, like how many ever zeros y contain, that many more zeros than ones. So this is not part of the language, but condition 1 says that x y y z should be part of the language. Okay, so this is a contradiction. Once again, we choose a string 0 power p, 1 power p, which is in the language and is of length greater than the pumping length. Condition 3 states that condition 3 implies that y is entirely zeros. Condition 2 implies that y is not empty. So y has at least 1 zero, could have more zeros, right, and does not have any ones. So now x y y z as per condition 1 should be in the language, but x y y z contains L more zeros than ones, which is a string not in the language, right. So we picked one string and showed that it cannot be split. This is the only way to split it meeting these conditions, but then again it fails in condition 1 if we try to forcefully satisfy condition 3 and 2, right. Hence this string is not in the language, which is a contradiction to the assumption that C was regular. Hence C is not regular, right. Okay. Okay. Couple of points here. The choice of the string is very important, right. So as I said earlier, this is usually the most creative, or when I say creative, it's not like extreme level of creativity or anything. It is usually the more the thing that where you need to like maybe think about couple of options and finally we'll figure out something. But this is very important as well, because if S is regular, all the strings can be pumped, right. All the strings that meet the requirement that S is in the language and S is of length at least p can be pumped. Even in this case, there could be other strings that could be pumped. So for instance, if you consider 0 1 power p, where 0 1 repeats p times, 0 1 0 1 0 1 0 1 like that p times. However, if you take x as 0 1, y as 0 1 and z as the rest of the string, this split satisfies all the conditions, assuming p is like something like 10 or more than 10 or something, anything more than 5 will work, I think. This satisfies all the conditions. If you see y is not empty, if you see x y is of length of length 4, which is of length less than, assuming p is at least 10, it's fine. And if you take x y power I z for any number of i's, all of this have equal number of zeros and ones, because x has equal number of zeros and ones, y has equal number of zeros and ones, and z also has. So even if you repeat y whatever many times, the number of zeros and ones equally get repeated. So this meets all the conditions. But we cannot use this to infer that the language is regular, because if the language is regular, all strings can be pumped, all the strings that are in the language and that are of length at least p. Just by showing one string that can be pumped, it is not good enough. To show that a language, so in fact you cannot show that a language is regular using pumping lemma. To show that a language is not regular, we just need to demonstrate one string that cannot be pumped. However, to show that a language is regular, it is not enough to show that some string can be pumped, right. So to show that a language is not regular, you have to carefully choose a string. It is not like you choose whatever string that meets the conditions and then you can get a contradiction, right. So here there is an example. You have to carefully choose a string, because if you choose a wrong string, that perhaps it can be pumped or split in the manner satisfying the 3 conditions. Okay. So this is very important, and hope you remember it when you are trying to work out exercises. Okay. Another point is we first showed that b, which is 0 power n 1 power n, is not regular. and I observed that B is a subset of a sub language of C, right. C has all the strings that have an equal number of zeros and ones, but B has all of them that take a particular structure, 0 power p, 0 power n, 1 power n. So B is a subset of C. Here there is another way to show that C is not regular, right. The another way is the following: if C was regular, then C intersection 0 power 0 star 1 star is also regular. This is because regular languages are closed under intersection. So if C is regular, we know by assumption C is regular. 0 star 1 star is clearly regular, right, because it is a regular expression. 0 star 1 star means the set of all strings that start with zeros, some zeros, and then followed by some ones. Okay, some zeros followed by some ones. Right. So this including 0 zeros are possible, some 0 ones are possible. Right. It could be some zeros alone, it could be some ones alone, it could be some zeros followed by some ones, but it will not have some ones some ones and then some zeros. Right. So this is a regular expression, and hence it is regular. So the intersection is also regular because regular languages are closed under intersection. But what is C intersection this? In other words, the set of C is a set of all strings that have equal number of zeros and ones, and out of these strings, which are the ones that take the 0 star 1 star structure? If you think about it, you will see that the only way this can happen is if we have some number of zeros followed by the same number of ones, which is exactly what we defined B to be. So C intersection 0 star 1 star, this is a regular language, and this happens to be B, right. So we have said that it is regular, and now we are observing that it is equal to B, but we have already shown that B is not regular. So if C was regular, this intersection is regular, but this intersection is equal to B, which we have shown to be not regular. Right. So this implies that, so we started with the assumption that C is regular, and we ended up with the inference that B is regular, which we know is a contradiction because we have already shown B to be not regular. So this implies that C is not regular. Right? So this is a way to show that C is not regular without directly going through pumping lemma. Right? So here we are just using closure properties. We are just using that 0 star 1 star is a regular expression. Regular, and 2 we are using that regular languages are closed under intersection, and 3 we are using that B is not regular. Right? So these are the 3 facts that we are using. Right? So maybe I will just list them down here. So 3 facts that we are using, maybe I will write it here, are 1, maybe I will not list them down because its space is a bit constrained. The first is that 0 star 1 star is regular, second is that regular languages are closed under intersection, and third is that B is not regular. So these 3 together imply that C is not regular, right, without directly applying pumping lemma on C. Okay. So this is just one example that is there in the book as well, but you can try it out. So set of all strings which are of the form WW. So basically you should be able to write it as a repeat of 2 strings. So 101 101, this is not of that form. Right? First of all, if it is a repeat, it will have even length, right? Even this is not of that form. But 101 101, so this is not in F, whereas this will be in F. So set of all strings that are of the form WW, where W is some string. So basically some string repeated 2 times. So this language is not regular. So this is just, I am just leaving it as an exercise. I think it is there in the book. Otherwise you can try to work it out. It's pretty much similar to what we have been doing before. Okay, so we took C, and now we will see one more language, which is a unary language. Okay, so unary language means all the strings in the language use only one symbol. In this case it is the symbol 1, right. So what is the language? D is 1 power n squared for all n. Okay, so let us try to write down what this language is. When n is 0, this is empty string. When n is 1, this is just 1. N is 2, it is like 4. When it is 3, it is 9, and so on. So basically it is set of all the set of all strings of 1s whose length, so entirely of 1s whose length is a perfect square, right. So 1, 4, 9, 16 and so on. So again it's an infinite set of strings, set of all strings whose length is a perfect square. Now the standard template applies. We assume D is regular, which implies there is a pumping length, and now we consider the following string S, which is of length p square, right. So the length, so all the strings are comprising of 1s, right. So the only so once I tell you the length, then you know the string, right, because it's p. When I say the length is p square, it just means that the string is entirely 1s. String is entirely 1s and string is p square 1s, right. So consider this string and we will show that it cannot be pumped. So if x, suppose we can pump it, right. So which means if S can be split as x, y, z, right. Then by condition 3 we have the length of x, y is at most p, right, which means the length of y is also at most p, because x, y is a superstring of x, y. So length of y is also at most p, right. So it follows that now the length of x, y, z, right, x, y, z, the length of x, y, z is the length of S, which we know is p square. This is strictly less than the length of x, y square z. Why is that? Because y is non-empty, right. So when you add one more y, you are adding something to the string, so it adds length, right. So like condition 2 says that y is non-empty. Now what is the length of x, y square z? What is the length of x, y square z? The length of x, y square z is the length of x, y, z and the added string y, the length of the added string y. Length of x, y, z is the same as the length of original string S, right, because that is what x, y, z is, which is p square, and then you add the y. But we know that we just said that x, y is at most p, hence y is at most p, right. So this is at most p square plus p. So the length of x, y square z is at most p square plus p, but this is strictly less than p plus 1 whole squared. What is p plus 1 whole squared? It is p square plus 2p plus 1, right. So p square plus p is strictly less than this. Okay, so we did some bunch of calculations. So what does it amount to? So we started by saying that the length of x, y square z is strictly greater than that of x, y, z, and the length of x, y, z is p square, right. So length of x, y, z is strictly greater than p square, and we ended by saying that it is strictly less than p plus 1 whole squared. So the length of x, y, z is strictly greater than p square and strictly less than p plus 1 squared, right. So it is in between two perfect squares, p square and p plus 1 squared, and we know that after p square the next square is p plus 1 squared. So it is lying between two perfect squares. So we know that this implies that x, y, z, maybe I will just use a different color here, this is not the length is not a perfect square, because it is neither p square not p plus 1 square, it is something in between. Hence x, y, z is not in the language, because the language consists of all the strings whose length are perfect squares. Hence this is not regular. Okay, so again we just to quickly recap, we assume that it is regular, so there is a pumping length. Now we consider the string 1 power p square, which means of length p square. Now by condition 3, we knew that y is of length at most p. Condition 2 tells us that y is non-empty, so y is something between 1 and p, the length of y. And then we reasoned to show that x, y, y, z is of length strictly greater than p square and strictly less than p plus 1 whole square. Hence the length of x, y, y, z is not a perfect square, and hence it is not regular, right. Another example or exercise for you. Consider all the strings 0 power I, 1 power j, some zeros followed by some ones, where the number of zeros is strictly greater than the number of ones. Okay, so this is strictly greater. Okay, so this is not the B, where B had the number of zeros and the number of ones were equal. Here we are saying it's strictly greater. This also is not regular. The one novelty that you will find when trying to do this is that in this case you will have to pump down, meaning pump down means in all these cases here we have considered x, y, y, z and showed that that is not in the language. Pumping down, I mean we will have to consider instead of x, y, y, z, x, y, y, z, we will show that x, z is not in the language. So x, z is also x, y power I, z, where I is equal to 0. So instead of pumping up, meaning adding more copies of y, we are pumping down, we are removing the existing copy of y. So this is why this example will be interesting. You can try it out. Okay. So finally, I think we have seen 3 examples. Just to summarize, maybe I'll just bring it a bit below. Just to summarize, what does pumping lemma? Pumping lemma says that if A is regular, right, then for all S, right, so for all S, maybe I'll have to edit this a bit, for all S in A such that the length of S is at least P, there is a way to split S such that x, y is at most P, y is greater than 0, and for all I, x, y power I, z is in A, right. So this is the pumping lemma again, so I am just reiterating it. So it has the following form, right. So there is a for all here. So for all the S, so if A is regular, for all the S, this has to be satisfied, right. Then there exists a split, right. There has to be some way to split it, right. So there could be multiple ways of splitting it, but all we require is some way to split it such that again there is a for all. So to show that a language is not regular, we have to negate this. So we have to show that there exists a string. So this string is entirely our choice. So instead of for all S, to refute for all S, we have to show there exists a string, and for that string, for all splits, this is not true, right. So for that split, for that string, we have to refute all possible splits such that these two conditions, and we just have to show one I for which this is not satisfying, right. So we in all the examples that we worked out, the I was 2. So we said that x, y, y, z is not in the language, but then there could be other cases too, right. So this can be thought of as a game. You tell me the language that you want to show it is not regular. I will pick the string. Now you tell me whichever split possible, then I will show you where that split falters, right. So I will have to show that it is my duty to pick the string, but whatever split you come up with, it will not be possible, right. It will not meet the condition. So whatever you come up with, I can find some issue with that split. So just summarizing, we demonstrated how to use pumping lemma. So this is the standard template. We assume the language is regular, then we choose a string that is in the language and that is of length greater than or equal to p, and show that the string cannot be split. Again and again I am repeating this. So the choice of string is entirely ours. We can choose any string that is in the language, but then we have to argue or reason that whatever way to split it, it cannot satisfy all the three conditions, right? So there is no way to split it as x, y, z satisfying the three conditions, and that yields a contradiction. So then we saw the three languages. First is 0 power n, 1 power n. Then is a set of all languages, all strings that have equal number of zeros and ones, which is a superset of the previous language. Then I said that you can also use closure properties to show that the second language is not regular, right? By just appealing to the fact that B is not regular, and by closure properties you can show that C is not regular. You don't have to go through pumping lemma, right? Even though we also saw the pumping lemma proof. And finally we saw the unary language proof, where we considered a unary language. And yeah, I think that's about it for this lecture, lecture 13. See you in the next lecture. Thank you.